In this video, we're not going to learn any new information. We're just going to examine different situations where the law of sines can be a useful problem-solving technique. We'll consider areas such as engineering parts, military operations, and even construction. Let's get started with example 3. It says an engineer wants to position 3 pipes at the vertices of a triangle. If the pipes have radii 2 inches, 3 inches, and 4 inches, what are the measures of the angles of triangle ABC to the nearest tenth? So notice that the center of each pipe is placed at a vertex of the triangle. The radii of each pipe are labeled on the diagram. But this boils down to a simple problem of solving a triangle. In order to find the angles of the triangle, we need to know the lengths of all 3 sides. Noticing from the diagram that each side is the sum of 2 different radii, we can determine the length of side AB by summing 3 inches for this radius plus 2 inches for this radius. That's going to give us a side of 5 inches. Similarly, this radius is 2 inches plus this radius, which is 4 inches, gives us a side of 6 inches. And finally, 4 inches here plus a 3-inch radius is going to give us a 7-inch side. So you can see we're dealing with a side, side, side triangle. In the side, side, side case, it's always a useful thing to begin by solving for the largest angle. The largest angle is opposite the largest side. So we'll label this as angle alpha, and it's opposite the largest side of 7 inches. We can solve for this by applying the law of cosines. We're going to square the opposing side and set it equal to the sum of the squares of the other 2 sides, minus 2 times the product of those 2 values times cosine of alpha. Now, because these numbers are easy to work with, I am going to go ahead and evaluate them this time. We have 49 equals 25 plus 36 minus 60 cosine alpha. 25 plus 36 is 61, and subtracting 61 from both sides, 49 minus 61 over here on the left is going to give us negative 12. We can then divide both sides by negative 60. Negative 12 divided by negative 60 is positive 1/5. So we can solve for alpha by evaluating inverse cosine of 1/5. With our calculator in degree mode, we find inverse cosine of 1/5 to be 78.5 to the nearest tenth. So our angle alpha is 78.5 degrees. And I'm going to go ahead and label that on the triangle, 78.5 degrees. Next, we can work on calculating angle beta using the law of sines. So starting with the angle that we know, sine of angle alpha, or sine of 78.5, divided by its opposing side of 7, is equal to sine of the angle we're attempting to find, beta, divided by its opposing side of 6. We can multiply both sides by 6. That's going to isolate sine of beta on the right, and then we can further isolate beta by applying inverse sine to both sides. With our calculator in degree mode, we evaluate inverse sine of 6 times sine of 78.5 degrees divided by 7, and to the nearest tenth, beta is then 57.1 degrees. Beta is 57.1 degrees, and I'm going to keep up with that information on my diagram. So here we have 57.1 degrees. The last angle we are looking for is angle gamma, and the last one's always the easiest one. You gotta love the last one. We're going to subtract our 2 known values from 180 degrees. The leftovers give us the measure of angle gamma. So we'll evaluate 180 minus 78.5 minus 57.1, and our remaining angle then is 44.4 degrees. So we used both the law of cosines and the law of sines to solve this simple problem. Often engineers have to uniquely define parts for machines that they construct, and so you can see how the law of cosines and the law of sines would come in handy in a situation like that. Let's try a different situation. Let's look at a military operation, for example, 4. A submarine sets sights on a moving target at a distance of 820 meters. A torpedo is fired 9 degrees ahead of the target and travels 924 meters in a straight line to hit the target. How far has the target moved from the time the torpedo is fired to the time of the hit? So the distance that we're looking for is this distance right here. Notice we're dealing with a triangle in which we know 2 sides and the included angle. This is perfect for the law of cosines. We can solve for this distance x by setting the square of that distance equal to the square of the sum of the squares of the other 2 sides. That's 924 squared plus 820 squared minus 2 times the product of those 2 numbers times cosine of the angle in between, 9 degrees. We can then solve for x by taking the square root of both sides. And remember, we're only recognizing the positive or the principal square root here, since it's modeling a distance. So plugging this into our calculator, we have the square root of 924 squared plus 820 squared minus 2 times 924 times 820 cosine of 9. To the nearest tenth of a meter, the distance is 171.7 meters. So x is approximately 171.7 meters. Very simple application of the law of cosines. Let's consider a construction problem like example 5. It says a tunnel is planned through a mountain to connect points A and B on 2 existing roads. If the angle between the roads at point C is 28 degrees, what is the distance from point A to B to the nearest tenth of a mile? Once again, do notice from the diagram that we know 2 sides in the included angle, so this is the side angle side case of solving a triangle. To find the distance between point A and B labeled x, we can easily apply the law of cosines. So we're going to set this up as 5.3 squared plus 7.6 squared minus 2 times the product of those 2 numbers times cosine of the angle in between, which is 28 degrees. As we did on the previous problem, we can take the square root of both sides, and this will give us an approximation for x in one calculation. Both of these problems are solved in exactly the same way, but they are 2 very different applications. To the nearest tenth of a mile, we get 3.8 miles for the length of the tunnel. Let's consider one last application where you might find the law of sines to come in handy. Example 6, the end of a steel shaft for an electric motor is to be machined so that it has 3 flat sides of equal widths. So looking at a close-up of a cross-section of the end of this shaft, there are 3 flat sides of equal lengths, and they're separated by an arc on a circle. It says the radius of the shaft is 10 millimeters, and the length of the arc between each pair of flat sides must be 2.5 millimeters. So the radius of the shaft is 10 millimeters. It's shown on the diagram, but we can also recognize that the distance from the center to the edge of the flat side is also going to be 10 millimeters. So we can construct a little triangle and enlarge it here to work with it. Both sides of this triangle are going to have 2 sides of length 10 millimeters. Our job is to find the width S of each flat side to the nearest hundredth of a millimeter. This would be a really simple problem if we knew this central angle alpha. Looking a little closer at our diagram here, notice we can get 3 congruent triangles by constructing radii out to the chords on the circle. The central angle of each of those triangles is alpha. However, we can't determine alpha by taking 360 degrees and dividing it by 3. And the reason is because we have some additional angles here that would make up that 360 degrees. Now, if I could figure out that angle, then I could also determine the unknown angle alpha. So let's work on this triangle right here. Notice we have an arc of a circle. I'm sort of emphasizing the arc. And the length of that arc is 2.5 millimeters. Recall way back from the beginning of the semester that the length of an arc, which is generally labeled as S, is equal to the central angle alpha in radians times the radius of the circle. Now, we don't want to confuse this formula with the S and alpha that we've denoted for this specific problem. So S again is the arc length. Alpha is the angle in radians. And R is the radius of the circle. To obtain the measure of this small angle here, we'll set the arc length of 2.5 millimeters equal to the angle in radians, let's call it beta to distinguish it from this alpha, times radius 10. So this angle beta is 2.5 divided by 10, or 0.25. It's really important to remember that when we use the arc length formula, the angle is measured in radians, not degrees. Now, if we take 2 pi radians and we subtract 3 times 0.25, then the leftover radians will be accounted for the blue triangles, one of which has this central angle alpha that we need to know. Taking 2 pi radians minus 3 times that angle beta that we calculated, we're going to come up with a leftover value of 2 pi, and I'm going to call that 3/4. 3 times 0.25, you can either write it as 0.75. I'm going to go ahead and convert it into a fraction, 3/4. So this is the leftover amount of radians in one rotation around the circle that can be accounted for the central angles of our 3 congruent triangles. We only need one of those. So notice that alpha is going to be 1/3 of this leftover value, 2 pi minus 3/4. If we simplify that, we can call that 2 pi over 3 minus 1/4. So now that we know our central angle alpha in radians, we can then either apply the law of cosines to find S, or we can use the shortcut formula for the length of the chord of a circle that we learned in the previous video. Recall that the length of the chord of the circle, which in this problem is labeled as S, is equal to the radius, which in this case is 10 millimeters, times the square root of 2 minus 2 cosine of the central angle, which we've calculated as 2 pi over 3 minus 1/4. You could also simply solve that using the law of cosines, and you'd arrive at the exact same calculation. Now, since I'm working in radians, I am going to need to switch my calculator to radian mode. About once this entire chapter will you have to deal with radians, and here it is. Calculating 10 square root of 2 minus 2 cosine 2 pi over 3 minus 1/4, and rounding to the nearest hundredth, we get 15.94 millimeters. So the length labeled S in the diagram is 15.94 millimeters. So that's a great set of applications for the law of cosines in machining, construction, and even military operations. They were all solved based on law of cosines, a very useful formula to know.